All right, so now we're going to turn to computing surface area. Now, before we can get into full-blown surface area of just any random generated surface, we're first going to tackle the problem of the surface area of a cone. And so here's how we do that. So here I have just a typical right circular cone. That cone has some radius r, right? Some radius r. And it has some height h. Okay. We also have this length right here, which we'll call L. Now here's the idea. First of all, let me notice one simple fact here, that L is equal to the square root of r squared plus h squared, because it is just a part of the hypotenuse of this right triangle here. And we have this right triangle with side length h and r, and so the hypotenuse by the Pythagorean theorem would be L equals r squared plus h squared. Now, what we're going to do is take a pair of scissors, mathematical scissors, and we're going to cut. We're going to cut this cone up that length L. And then we're going to fold it out and see what we have. And I want to show you two visual examples of the thing we're going to get. Here, if I look at my camera here. Here I have two cones. You can kind of see it a little better if I push down on it a little bit. And my other cone. And if I push down, you can see it's more cone-shaped. And these two things were generated by just taking a circle and slicing out a section. And that's actually what we're going to get when we unfold our cone that we have here. Is we're actually going to have something that looks like this. Well, pencil out. And what we're actually going to get is something that looks like this. Okay, we're going to have a circle with a chunk out of it. Now, the outside length of this circle, will still be the same as the piece here, because I'm just slicing the R and opening it up. So the outside piece along this circle will be 2 pi r, right? The circumference of the original cone. Okay. And of course, this length will be a length L, right? Because that was the length that we cut along. So this will be a circle of radius L. The cone will actually be a sector of a circle of radius L with an angle in radians, central angle of theta. Now we know a few things about circles and arc length. So this length here, this 2 pi r, is the arc length of this circle of radius L with a central angle theta. And we recall that the arc length of a circle is S equals r theta, or in this case, L theta, but the arc length is 2 pi r. So therefore, that means the central angle is 2 pi r divided by L. Now you might say to yourself, well, how in the world does that help me? Well, we also have a formula because we want to know the surface area of my cone, but the surface area of my cone will actually just be the area of this sector of a circle. And so we have a circle of radius L, and we have a central angle of theta. And so we have a formula from trigonometry for the sector area of a circle, and that is that area is 1/2 the angle in radians times the radius squared. So putting in our angle that we now have in terms of L and R, we can now get 1/2 of theta, 2 pi r over L times L squared, and then we simplify that. And we find that the area of the cone will be pi r L. 1 L cancels out, the half cancels out, and we just get pi r L. Now that's the area of a cone. So the surface area of a cone is pi r L, but remember L is the square root of r squared plus h squared. So if you know the radius and the height of your cone, then you can actually figure out its surface area by just taking pi times r times the square root of r squared plus h squared. Okay. So that's the first idea. Okay, we have to talk about the area of a cone. Area of a cone. Now, we talk about the area of a cone so that we can move on and talk about the area of another special shape that's based on a cone, a shape called a frustum. So let me draw the picture here for you. Let me draw the picture here for you. Get my dotted line out here to work. And again, we're going some radius r. I'm just going to copy that. Oops. Copy that. And make sure I have the same radius on the other side. And generate my cone. Okay. And so now I have my cone. Okay. And then what I'm going to do is take the cone and chop it off. So that we basically chop the top part off the cone. So that we just have this shape here, right? Which to me always looks like that thing they have at the circus, that the thing they have at the circus that they put the animals on. That's what it always looks like to me. This thing is called a frustum. This thing's called a frustum. Okay, so we want to figure out the surface area of this frustum. Okay, we want to figure out the surface area of this frustum. Now we need a few more points about the frustum. We need a few more points about the frustum. So to get to that idea here, I want to put in a little bit more information here. So to talk about this area of the frustum, first of all, this thing is called a frustum. So get myself off track here. And we're going to talk about first two cones. We're going to talk about the really big cone here, and we're going to talk about the really small cone here. And So I want to talk about the surface area of those two things, because if I can talk about those two things, the big one and the little one, then I can just take the surface area of the little one away from the surface area of the big one, and that'll be the surface area of my frustum. Okay, so we need a little bit of information here. So notice that this side of the cone here is a straight line, so we could actually generate the cone by taking that straight line and then just revolving it to get the solid that's a cone. So that equation is just a straight line, and we can even put the tip of it at 0, 0, so that the frustum, or the cone here, is generated by some straight line with slope c. And then we would have 2 points that we want to mark on our cone. The bottom point for the small cone, which is A, f of A. And over here, the bottom point for the big cone, which is B, f of B. Okay, so first thing, in terms of this function f of x, I want to talk about, I want to find a formula for the surface area of the cone that starts at 0, 0 here and goes to B, f of B. So starting from above, S sub B would be pi times the radius times the length, which would be pi times the radius times the square root of r squared plus h squared. Okay. Now, in this problem, the radial length r, sorry, not radial length, I'm not getting a radial, the radius of my cone is just f of b, right? The radius of my cone is just f of b. So plugging in b for f, I would just have CB, so that's what r is, and then also I put that in for r squared. And then the height of my cone is just b. So putting all that together, I have pi times CB times the square root of CB squared plus B squared. So what I'm going to do here is factor out a B squared. So I'm going to have pi CB square root B squared times C squared plus 1. And then square root of B squared is just B. So the result is that the surface area of the B cone is pi B squared C square root C squared plus 1. Yeah, ugly. Very ugly. Likewise, though, we could do the same thing and get that the surface area of cone A is pi A squared C square root C squared plus 1. Okay. All right. So finally here, we get that the surface area of the frustum is, call it S sub F, SA, SB minus SA. So pi B squared C square root C squared plus 1 minus pi A squared C square root c squared plus 1. And we simplify that by doing a little bit of manipulation. And we get that, well, that c and square root of c squared plus 1 and that pi, they're in everything. So they can be factored out, and all that's left is b squared minus a squared. Okay, so we get pi c b squared minus a squared times the square root of c squared plus 1. Now we could substitute in for b squared and a squared, all right, so that they're, well, actually we can't, they're our values. Sorry, ignore that thought. So that's kind of ugly, right? That's kind of ugly. It's pi times c, the slope, times the difference of b squared minus a squared, times the square root of c squared plus 1, again, c being the slope. So that's kind of ugly. Until we go back to our problem and say, okay, what's the length of my frustum? What's the length of my frustum? Okay, what is the length of my frustum? Okay, because when we talked about the cone, we had the formula in terms of length, pi r l. That was a pretty simple formula. So let's go back and investigate the length of my frustum. That would just be the length of this line segment. We can just simply do that by the distance formula. So kind of ugly at the moment, but it's going to get better. So now L, the length of the frustum, by the distance formula is the square root of difference of the x's, so b minus a squared, plus the difference of the y's. Remember, that's BC minus AC squared. Okay. But that can be rewritten as the square root of B minus A quantity squared plus B minus A quantity squared times c squared, because I can factor the c out and then square it. Well, then I can factor the b minus a stuff out and do the square root of it. Now, normally that would be absolute value, but in this example, b minus a, because of how we set it up, is positive. So that would just be b minus a times the square root of c squared plus 1. Okay. So now if we go back now, to our S sub f function here, that was pi c b squared minus a squared square root of c squared plus 1. So now we're going to take the result that we just had here for L, and we're going to use it to manipulate this frustum thing into something that's a whole lot simpler looking. So here's how we do it. So we start with S sub f equals what it was, pi c b squared minus a squared square root of c squared plus 1. And we factor b squared minus a squared. Pi c times b plus a times b minus a times the square root of c squared plus 1. But this piece right here can all be replaced with L. Can all be replaced with L. And then this other piece I'm going to manipulate just a little bit. Pi times BC plus AC times L, but BC plus AC, BC plus AC is just f of B plus f of A times L. And now we're ready to look at it in terms of our approximation step. So the whole reason we were looking at frustrums, the reason we were looking at this thing and we wanted a formula for the surface area of that is because if we have some curve, here, right, and we're revolving that, and we want to, generate our, solid. Well, what we're going to do on that cone is we're going to take and subdivide it, and we're going to compute the surface areas of those different. All right, we're going to compute the surface area of these different frustrums. And when we do that, we can measure the length of the side by using our arc length. Okay, so that on our approximation step, the surface area of the ith estimation is just going to be 2 pi f of xi times the length. Okay, and we can do that because since these things are so close together when we eventually do our integral and approximate, then we just double f of xi instead of having f of xi plus f of xi minus 1. We just double it, because once we go to infinity, it's not going to matter. So that finally, after all this work, the surface area of our shape is the integral from a to b of 2 pi f of x times the arc length, which is the square root of 1 plus f prime of x squared dx. And so now we have the surface area. Right? We now have the surface area formula. So this was a long process. So definitely not something I'd expect you to repeat, but I hope you were able to follow it and understand it. Right? So the first idea is we took a cone, we sliced it along its length, okay, break it apart, and that basically gives me like a pizza with a slice taken out. Okay, we were able to do some manipulating, eventually get that the area of the cone can be given by that formula. We then turned to a cone with its top cut off, which is called a frustrum. Right? And from that object, we were able to work out, through some computation, the formula for the surface area of a frustrum, which was a very messy formula. Okay? But then when we went back, we computed L, and we were able to do some factoring on our frustrum formula, and do some changing to bring in L. And then the rest of it just turned out to be pi plus pi times the sum of the two values there, the two radiuses. And so, since we're doing sums, and we're going to let everything go to infinity, instead of doing f of b plus f of a, we can basically say it's just really the same as the two values there on our approximation step. And then we add them all up. And so we get 2 pi f of x, and then the arc length formula. So it turns out surface area is actually going to involve the integral of 2 pi function and the same piece we would have done for arc length. Okay, so in upcoming videos we'll actually see some examples of this, and it'll be a lot easier to use than it is to actually come up with it. Okay.